Hey guys, welcome back to AP. Um, it feels like it's been such a long time since 8A, right? I don't know, break felt longer to me. I don't know about you guys, but it felt a bit longer to me. But hey, great to be back. We're now in AP, the better of the two classes. And hopefully by the end of the course, you guys feel the same. Um, I know we were supposed to meet like live, but a lot of things have been changing for me this month. New things happening, new opportunities, stuff like that. So it's hard for me to be flexible. Like I know I literally said like 2 days ago that I was available at like 4 or 5, and now I'm not available just because something just came up. Um, so I think recordings like this are going to be very useful. Not only just because I can make them whenever, you guys can also watch them whenever, and you guys don't have to wait for me to, be able to meet at some time and maybe actually have to cancel or anything. So maybe this first one and then maybe the next one, or for sure this first one, but the next one might also have to be just a recording. Not too bad. Maybe sometime in the quarter we can all sit down and have a nice chat in live. I like live meetings, honestly. They're a lot more fun, and everyone gets to talk and struggle together. That's always really nice. And I like talking to people. I don't like talking to myself. So anyways, cool. So actually, I guess for those of you that don't know me, my name is Timothy. I go by Jim in a server. I'm a fellow student in this class. And these videos or these recordings, really their main purpose is just going to be to make the material more accessible. I know that, OChem is not exactly the easiest thing, but, you know, having more resources is not going to help, or sorry, is not going to hurt, is what I meant to say. Having more resources is not going to hurt, especially in a class where, doing as much practice, like in AB, really my mantra is do as much practice as you can. Um, you know, get to the point where you kind of just instantly see your transformations. That'll make your life a lot easier. Okay, cool. So all this is meant to do is just help you see those transformations, and tips and tricks on how to do these things faster. Okay, cool. So for this first one, we'll talk about alcohols. Normally you guys talk about alcohols and ethers for the first quiz, but you guys have only gone up to alcohol, so that's great. Makes this first quiz a bit more manageable, and kind of help you ease your way back into thinking organically, thinking about how electrons want to move and how they want to react. Just want to get this out of the way. So I know every section you guys learn nomenclature, especially in alcohols, you learn nomenclature. I can't teach that to you guys. It's not that I can't, I just won't. I'm very against nomenclature. It's a very obsolete skill. Rather than spending years explaining why, let me just show you guys why I think it's obsolete. So if you navigate to this, you can find this easily. Just put in ChemDraw. If you put in ChemDraw, free sample page or whatever, literally just this, actually, I don't know why to just go up here to here. Just put this in. You'll find this page. Let me just show you. Just, go on here, just draw something crazy random. That's not going to work. Look, I'm just going to draw something crazy random, right? I mean, if you think about like PhD level work, so work that your professors have done, work that your TAs are going to do, blah, 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 whatever. Right, just something random, something that like maybe would take a couple hours to name on your own, right? I'll throw in alcohol just because that's what we're learning about. Imagine this is what you're working on. I don't know, you probably wouldn't, but maybe something like this. Let me just put a bromine on here, okay? And you have to think of a name for this, right, or figure out the name. Guess what? I press space, I navigate up here. Wow, I pressed one button, and this gives me the most correct name in IUPAC, right there, right then and there. This is the most correct name via the most current IUPAC Blue Book. So anyone who tries to convince you that nomenclature is a good skill to have or that it's useful, I don't really agree. I don't agree that naming complex things is really useful. I do agree that there are a couple groups you should know, right? Just the name for them, like what an alcohol means or what a bromine means, a bromide, alkyl halide, right? Stuff like that. I will never be convinced that you need to be given long molecules that need to be named. Maybe one that's more realistic for you guys is something like this, right? Like these tricky ones where how you number and which direction you go in matters, right? Like I don't believe any of this, because guess what? If I were to describe this to somebody, right? If I wanted to describe this molecule to somebody, you know what I would say? I would just call it an alkenol, or this is a 7-membered ring, so hept. So cycloheptenol, that's what I would call this, because it's a cycloheptane, it's an alkene, and it's an alcohol. right? Maybe I even throw in a bromocycloheptanol because I see that, right? I'm not really concerned about the actual name. So I needed the actual name for a paper. I would just hit this button. Look at that. Wow, that's right there. 2 seconds, not even 2 seconds, 1 second. I got the name. Okay, I did not need, there is no need for me to sit down and name this, assign SNR and all that stuff. I understand why SNR is important. I just don't understand why naming is important. So again, it's not that I don't have the ability to teach you how to how to teach nomenclature. Maybe I don't. I'm okay if I don't, but I choose not to even learn it because no scientist in the world I know actually sits down and names these things. They sit down on their computer and they draw this up and they hit that button. And this is the free version, right? The free version gives this, so you guys can do this too. So next time a TA or a professor tries to nag you guys and they're like, oh yeah, nomenclature is a good skill, just ask them, oh yeah, and what about chemdraw, right? Send them to this page. Tell them why this, why does this exist if nomenclature is such a good skill, right? It's really not. Knowing functional groups is good, but knowing naming, not that great, okay? So I can't teach you nomenclature, unfortunately. I refuse to, it's my silent protest. But I can give you a couple tips because inevitably, you guys are gonna have to learn anyways. But alcohols and naming, right? They always get priority because they are what we call suffix modifiers. So what does that mean? So back when you guys learned about things like butane, right? If I threw like a bromine or a chlorine or whatever, like, right, you guys fought over who got priority, right? And it was like, oh, alphabet, oh, number, blah, blah, blah. And, usually it was numbering, right? If there was a tie, it was alphabet. And you would put them over here, right? Bromo, chloro, whatever, butane. Well, if I change, let's say, this bromo into an alcohol, well, this is no longer a butane. This is now a butanol. But what in the world just happened? My drawing pad just like, what? It like changed speeds or something. Oh, whatever. I'll have to figure it out. Anyways, this is now a butanol. Okay. And so butanols, right, that suffix part there, that is a suffix modifier, right? Because it modified the suffix. That now gives priority. So we want the lowest number to be the one that corresponds with the suffix modifier. So now instead of, caring about, before when it was a bromine, we cared that it was 1 chloro, right? Now we care that this is 2 all, I guess, right? You would call this a but and 2 all. Okay, so suffix modifiers always get highest priority. Now, obviously, the question then becomes, oh, wait a minute. What if we then turn this into an alkenol, right? Because alkenes also are suffix modifiers, right? Now this is a butanol. General rule of thumb is the rightmost thing in the suffix modifier gets the highest priority. So alcohol gets the highest priority because it is the rightmost suffix modifier. Then your alkene, and then everything else. So rather than doing 1, 2, 3, 4, right, which puts alkene at 1, you are actually going to do 1, 2, 3, 4, which puts alkene at 3. Okay, so that this gets 2, this gets 3. Okay, so just always prioritize your alcohols. I guess the worst thing you could probably get is whenever you get like a ring or something. Remember that rings can also be substituents, especially if the alcohol is not on the ring. So let's say that this ring could be anything. I can even specify it, right? Maybe I make it a triangle or something. Instead of calling this a cyclopropane, this will be a cyclopropyl substituent, right? It would be a 1 cyclopropyl, right? Blah, blah, blah. I'm not going to write it out. 2 butanol or butan 2-all, right? I always recommend that you put the number inside the name rather than, I know sometimes you can do this, 2 butanol, right? You can do that instead, 2 butanol, but I don't recommend you do that. Put it inside because again, when you get to higher complexity and multiple suffix modifiers, you're going to already have to put it inside the name anyways. Like correctly, this would be butan. So this would be but 3N2-all, right? You can't just put a number in the front here. Okay, cool. So that's my 5-second spiel on nomenclatures. All you guys are going to get out of me. I hate this thing. Don't give it too much power in your studying. This is like last minute studying. This is like whatever. Okay. But that, guys, I'll give you guys that. But let's actually get into the chemistry of alcohols, right? Because that's what we care about. We want to know how these things work. Okay. Now, usually with these topics, you start with a little bit of the physical properties. definitely the case with alcohols, right? So one of the best things we can start with is to look at first water, right? I mean, water, that is an OH, right? Alcohol we think of as an OH. But water has two OH bonds, right? So it's not technically organic. But you know, it is a cool thing, right? Water, it's a very polar thing. If you think about water in respect to itself, right? Water has this very nice dipole where we have this positive, we have this minus. And so these positives and minuses can interact in hydrogen bonds, create these intricate systems, right, of these coordinated oxygens and hydrogen, coordinated water molecules, really. And so a lot of when we talk about polarity, or if we think about if something is polar, right, we like to think about, okay, can it hydrogen bond? That's usually a very good indicator, at least in the organic world. How can I tell if something is going to be highly polar or not? It's like, oh, can it interact in a hydrogen bond somehow? Because we're just, you know, we're thinking about water. Okay, but again, water isn't organic, right? It is just water. So how can we make water a little bit more organic, or how can we make organic water? Well, let's just replace one of those hydrogens with an alkyl chain. I'm just doing a 2-carbon chain here, right? So actually, let's see if I can put that this is water up here, put some names. But this here will be ethyl alcohol or ethanol. A couple of you are probably very familiar with ethanol. Hopefully as familiar as you are with water. Hopefully you guys are drinking both. Don't just drink one, drink both of them. Okay, they're very good. You know, and as a combination, they're good for you. Okay, cool. But alcohols are, you know, I like to call them organic water, right? And that's something that everyone likes to call them too, because that's really what they are. They are OHs just with a, you know, an alkyl chain attached to them. Okay, so maybe the first thing we can talk about is the polarity of this, right? Is okay, water is highly polar. So what about alcohols? Well, alcohols are also polar, right? They have that same OH, right? So if I think about an alcohol, right, at least, you know, if I draw like not the whole thing, but just a little bit of it, right, we do still have these hydrogen bond experiences, right? That's pretty good. Where they kind of suck, I guess, is, you know, hey, look at that. We have these alkyl chains. So these aren't exactly the most polar things ever. They are somewhat polar, right? They are there. I'll just call them polar, but we do have these hydrophobic non-polar carbon chains, okay, that are attached to them. And these guys are really going to interfere. Okay, so we have these non-polar chains. Okay. Non-polar chains. Now, the general rule of thumb is that if the chain is pretty small, like if it's less than 3 carbons, sorry, that's greater than. If it's like less than 3 carbons, it's usually very polar. You know, we think that it's highly soluble in water. So again, remember I mentioned that thing. Usually a good measure in the organic world of if something is polar, you think about how soluble it is in water, because water is highly polar. So if something dissolves in water, that thing is usually polar. Think methanol. So methanol is just CH3OH, right? Methanol, ethanol, propanol usually is also very soluble in water. Those things are pretty polar. But when we get to larger things like butanols, I mean tert butanols, you know, pentanols, I mean these really long chains. I mean the chain starts to kind of outweigh whatever polar component you have, right? We have more carbon chain than we have alcohol interactions. So usually things that are larger than 3, I would even say larger than 4 or 5. But my general rule of thumb is anything larger than 3, not very polar. Those are venturing on the, you know, the land of non-polar, right? I mean, think about it, right? Like if I had something like this is actually something I've worked on in the lab. But if I had something like this, actually, sorry, not like that. Let's just do this. Let's say I had something like this. So this is an alcohol that's very near and dear to my heart. This alcohol. Okay. And then this could be anything. Would you guys consider this to be polar or non-polar, right? I mean, it is an alcohol. Look at that. Look at that steric bulk. Look at this. I mean, this is a sterol. This is a steroid. Or actually, no, I guess sterol is the better term. Let's just call it sterol. But sterols are very non-polar, very non-polar, despite having one alcohol in them. Okay, so usual, you know, general rule of thumb, anything less than 3, right? So I guess maybe we can take an alcohol and we can say, okay, what if I took out that last hydrogen? What if I turned it into 2 alkyl chains? So I turned it into this here, right? This is diethyl ether. If you've ever smelled an ether before, ethers are very fruity. What's really funny is whenever we whenever we talk about ethers, like as a solvent, we call them, or as anything, we call them ethereal. And so a lot of people, when they see this, they think ethereal, like, stars and fairies and whatnot. They think ethereal, right? I'm not gonna write all that, but you know what I mean, like the spaces between every letter. And that's kind of how it smelled. They do smell kind of good. But anyways, this is diethyl ether. Another way to write this is Et2O, signifying two ethyl chains and oxygen between them. So sometimes you might see that. We consider this barely polar. Okay, barely polar. I mean, there is an oxygen, so it has that polarity component. But when we're thinking about like hydrogen bond experiences, I mean, it can't hydrogen bond with itself, that's for sure. Maybe if there's like a little bit of water, we can have a little hydrogen bonding, but it's, we have now, instead of one alkyl chain, we have two alkyl chains that are experiencing or introducing these non-polar effects. Barely polar. They are polar, but just barely polar. So because of that, there's actually some really cool things we can do with ethers because of that. One really cool thing we can do is that because they're barely polar, so they're mostly non-polar, if we need to dissolve a polar thing and a non-polar thing in solution, use an ether, right? Ethers are non-polar, so the non-polar thing will slip in easily. But because of that bare polarity, like it's very barely polar, it'll actually also solvate that polar thing too. Pretty cool thing. So ethers are pretty good solvents. They're also really good solvents just because they're really inert, because they're barely polar, right? Think about a butane that's not polar at all, right? We don't expect any reaction on that. There's no reaction we can do, right? We need some kind of polarity, we need some kind of functionality. Ethers are kind of the same way in that, yeah, we do have an oxygen, but it's barely functional. We have to use very strong conditions to do anything with them. Ethers, if you were in a higher class, you would learn as a very good protecting group or a very good resilient group. And at least in this class, we will learn that they are very good solvents. Okay, nothing can really crack open the shell of an ether other than very strong acid, thing that like eats your hand, right? Cool. So in terms of polarity, right, water is the most polar, and then alcohols, depending on the length of the chain, can be polar, or they can rise to very non-polar things, right? Like I drew that that's that sterol of that mine that I'm really oh, I guess I forgot this alkene here. But this is a very important thing to me. At least it was when I was working on it. Not very polar, right? But general rule of thumb: methanol, ethanol, propanol, polar things, highly soluble. Now, hydrogen bonding, right, also affects another physical property other than polarity, right? It also affects boiling point. When it comes to boiling point, right? Maybe we can go to, well, listen, maybe if I can fit stuff on here, if not, I'll put the next slide. Boiling point, right? Which is just, taking a liquid and exciting it into its gaseous form, right? Part of that is just, inserting enough energy into these molecules that we can excite every single bond. Now, when we think about the bonds of an alcohol, right? The obvious bonds are, the bonds that we see. Same thing with water, right? The obvious bonds are the ones that we see, right? The bonds between O and H, and here carbon O and H, right? And so exciting those bonds, it might just be a function of, what needs more exciting. But remember that things like water, things like alcohols, these guys participate in hydrogen bonding. So that's a sort of non-direct, or, not a very obvious bond that we have to break through as well. So not only do we have to, burn through this, right? Burn through this to get it excited. We also have to burn off these interactions too. At least introduce energy to, sort of pull back on those interactions so that we can allow these guys to excite into gaseous form. Okay, so water, I mean, everyone hopefully knows this. Water, we say, boils at 100 degrees, right? Boils at 100 degrees, okay, Celsius. And if we kind of treat it as sort of a like neutral standard point, right? And we can kind of look at these other things and see where they should fall. Alcohols also have hydrogen bonds, but if we think about in terms of, how many hydrogen bonds we have, it's not as many, right? So for these smaller alcohols, again, methanol, propanol, ethanol, maybe, I'm not sure about propanol, to be honest, but for sure methanol and ethanol, those guys are pretty small and they don't have as many hydrogen bonds as they do as water does. So these tend to have lower boiling points than than water does. I don't remember the exact value off the top of my head. I'd have to Google it. Actually, I mean, if I had to guess, maybe like 70 or 80 degrees on ethanol. I don't know. I'm not too certain. I'm trying to think of in lab if I've ever had ethanol start to boil, what I would have it at. Oh man, I bet the cooks who are watching this know, because sometimes you put alcohol and you burn it off. And probably know what temperature your pan is at. I'm not the greatest cook, so I don't know. I would say, I mean, it has to be less than 100, I would say. Probably like 80 degrees. I don't know, whatever. I'll just guess 80 degrees. No big deal. I would say like 80 degrees on things like ethanol, and methanol will be lower. So maybe methanol is like 70 degrees. But anyways, it's lower because, you know, we don't have as much hydrogen bonds. But once you get to these higher order, larger, you know, alcohols that have like a lot of carbon, the weight of the carbon having to burn through that outweighs any, you know, anything you had to do with the hydrogen bonding and water, whatever, and alcohols, whatever. So usually those guys are a bit higher than water. I don't think you'll ever have to order boiling point, but it could be a good vocab question, right? Like smaller order alcohols will have a lower boiling point, right, than water because of significant hydrogen bonding, but higher order, very large alcohols easily going to have higher boiling points, very, very easily. Remember, boiling point is, again, it's burning through each of those bonds so that you can excite them. So if you have a lot of bonds, you're just going to be a lot harder to excite than normal, right? With that being said, then actually let's finish this up and then we'll move on to specifically alcohols. Ethers, then, I mean, no hydrogen bonds at all, right? These guys are going to be obviously the easiest, and I actually have very good experience with this. Diethyl ethers easily, I don't remember the exact number. I'll say 30 degrees, and the reason why I say that is because diethyl ether will boil in your hand. I know you're probably thinking, oh my God, doesn't that hurt? You're probably thinking boiling water, right? Because boiling water is at a high temperature. That's why it hurts your hand. But diethyl ether, you splash it on your hand. By the time you look down to look at where it's splashed, it's gone. It's gone. Your body heat will melt it, or sorry, not melt it. It'll boil it. That's how like easily volatile these compounds are. So diethyl ether smells good and it boils really fast. Usually around 30 degrees Celsius. I don't, you know, I imagine leave-ins. I should check the notes. But I imagine leave-ins will give you the actual values. Those are the ones you probably want to know. Ethers, I know that they're at least 30, and I know that what I've given you is at least a value. So I can give you good ballparks. If you need actual values, go to the professor, right? They're the ones that are grading your exams and stuff, right? Cool. All right. So in terms of physical properties of just comparing alcohols to other known species, right? That's kind of what we see. But if I kind of look exactly at alcohols, this could be a good question, right? Asking you to order alcohol boiling points or whatever. Again, if I have different level alcohols, there are some things I can look at to kind of tell which ones are better and which ones are like, you know, more likely to boil, you know, faster than the other. So again, back in Gen Chem, hopefully you guys remember like the sort of crowding rule. Things that are very linear, I guess not the crowding rule, but like opposite crowding, but things that are very linear, right, tend to be more, you know, higher boiling point because you have to burn through every single individual bond. The way I think about it is like if you're lighting a fire, right, you have to burn through every single bond, right, to excite every single bond, right, and then this will go up in gaseous form. When things are really clumped, though, wait, hold on, 1, 2, 3, 4, 5, 1, 2, 3, 4, yeah. So both of these are 5 carbons, right? That's what I seem to do. But when things are really close, though, let's say I start to burn on a line here, right? Well, maybe that flame catches on this guy here, and this guy starts to preliminary burn. Maybe not a lot, but it starts a little bit. And so, you know, hey, we're close to this bond, maybe this bond starts to burn. So you need less energy to burn crowded, you know, bulking bonds because they're kind of helping each other out, right? The heat of burning one bond is kind of reaching the others. So they're kind of helping each other out. So this guy, you know, maybe this here is a forest and that forest just burns faster because they're all next to each other, which is really sad. We don't want our forest to burn. But this guy here, right, we have a little more time to save it, right? Because, you know, it takes a while to burn through every single individual, all 5 bonds individually have to be excited, right? This guy, I mean, if I start to burn a little bit on this guy, right? This guy starts to burn, this guy starts to burn, right? So yeah, so clumping branching, whatever you want to call it, those guys, as long as they're the same number of carbons, those guys compared to their linear counterparts have lower boiling points. So between these two guys, right? So this is again 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 carbons each. This guy will have a lower boiling point, right? Versus this guy has a higher boiling point. Okay. Now remember that boiling point again is a function of how many you have to excite these bonds. So if you have a lot of carbons or less amount of carbons, that can also just determine whether you're going to boil faster or not. So yeah, this guy is linear, but it's also just 2 carbons in an alcohol. This guy is obviously going to be the lowest out of all of them. There's just no way, right? So if I had to number these, right, this would be the highest, second highest, this would be just the lowest. It's not that hard to excite 3 atoms or 4 atoms, I guess, or I guess, sorry, 2 carbon atoms in an alcohol, right? But this is 5, 5, 5, right? This is gonna be a lot harder to burn through. You really gotta put some energy into that system. Okay. So yeah, so that should be the most you'd want to know about physical properties. I'm not sure what else you'd want to know. But that is what I can remember off the top of my head. Cool. So we'll just keep it on that then for physical properties. If there's anything else, let me know if I missed it, and maybe I'll comment on it somewhere. Again, these are meant to be supplements, so I can't make. I'm obviously not gonna be able to get everything, but I'll get the stuff I think is important. I think this stuff is important. But with that being said, let's just get into like reactions, or at least how we should approach alcohols in their reactions, right? So back in AA, we talked a lot about alkyl halides. So alkyl bromide is the best version of this, okay? And so the alkyl bromide, right, as a substrate was insanely good, right? Remember that if I were to put a nucleophile, whether it is a strong base or a weak base, our reactions just work incredibly well, right? So I will do weak base and strong base, right? Remember, weak bases, these guys preferred SN type reactions, substitution type reactions. So we saw that working very, very well. Bromides, I mean, halides are very good leaving groups, right? Very, very good leaving groups. So I'll put here, good leaving group, right? They're very acidic. So acidity wise, high up there, right? They're very, very acidic. So these guys are really, really good. If I had a strong base, right, maybe something strong, and maybe what I'll do is I'll put this here so that it's secondary. We could get like an elimination type reaction, right? So we get our E2. Remember, strong bases, these are going to be elimination because eliminations require a proton transfer or proton abstraction or acid base reaction. So that's kind of like the key. But if you use a strong base, usually if you want to do an elimination, weak bases, you're usually doing like some kind of substitution. Point is not to remember all this stuff. The point is just to kind of remember bromides, alkyl halides, they were perfect. They were great leaving groups because they were very acidic. And if you kind of just threw a nucleophile at them, they did the job that you wanted them to do. Very, very great. So when I take an alcohol and try to do these reactions, right, and I say, okay, let me take a weak base. Right, so I take a weak base nucleophile. Well, guess what? Nothing happens. So our SN reaction doesn't work. Okay. If I take, let's say, a strong base. So let's, if I use that strong base nucleophile, oops, let me be congruent. Right, strong base nucleophile. Guess what? It's not that this doesn't work, but the strong base is going to do something else. Instead of taking the CH, right? Instead of doing that, what it's going to take is the OH, right? OH is a more acidic bond, right? Having an O minus versus a temporary C minus, technically this is a C minus here. That is a much more acidic, that's much more stable thing. So strong bases, all they can really do is just pull off protons. So that's not very good because that's not, again, it's not doing the reaction that we want it to do. Okay, so what gives, right? Why is it that we don't see the SN2? I mean, we can tell why we don't see the E2, right? It's because of the acid base that we talked about. The acid base here is stronger than it is here, right? So it's way more likely to take off here. But why doesn't our SN2 work? Why doesn't that reaction work, right? What is inherently wrong about the alcohol that it won't do it? Well, if we kind of, again, compare the acidity, right? Br minus is a leaving group. That is very, very acidic. But if I think about what it'd be for an alcohol, that'd be OH minus. And if I look at the pKa values, which are like some absolute values that tell me about the acidity, Br minus is a negative number. It's like -8. If you guys, for those who don't remember, pKa, the lower it is, the better. Okay, the lower the pKa, the better the acidity. I know it's a bit weird, right? Scientists didn't really make this easy for us. But the lower the number, the better the acidity. And this is a negative number, right? So it is incredibly acidic, incredibly acidic. So it is a very good leaving group. OH minus, on the other hand, so the alcohol leaving group, is actually at 15. So not only is it a positive number, it's not even a low positive number. Like, so it's not even like 1 or 2, it's 15. This is incredibly bad leaving group. Very bad leaving group. And so if I try to do any of my reactions, whether they are E reactions or SN reactions, they're just not going to work because our leaving group is not going to leave at all. Okay, so OH minus, very, very bad as a leaving group. And bromides, right, very, very good. So maybe the solution is give up, right? Maybe let's just close the chapter on alcohols, right? Who cares? I mean, if they're not going to do the reactions I want them to do, right, then why even use them? Just use the bromides. Well, one is that that's not practical for the class, right? We have to learn about alcohols. The other thing is that actually turns out alcohols are a lot more abundant than bromides are. So maybe in the lab, you're forced to use an alcohol. It's cheaper. It's cheaper to have an alcohol than have a bromide. Okay. So what can I do other than giving up, right? What can I do to my alcohol? Well, we did just say that bromides are great, right? They work. They are incredibly acidic, great leaving groups. The only issue is that OH is not a good leaving group. So what if all I do is turn OH into something? So maybe I put in something G, okay? Some group that turns this alcohol into, this here, it says OG. So you might think, oh, it's still an alcohol, this has a G on it. But whatever G is, it turns it into a better leaving group, okay? So OH and OG are different, right? OH is alcohol, OG is some group. And this group mimics Br in the leaving group ability. So it mimics the Br leaving group. Well, hey, if I can make it that leaving group, then maybe it will do the reactions that I want it to do, right? Because I mean, that's the issue, right? It's not bromine, right? Alcohols have to become bromine, unfortunately, right? They don't have, they don't have the ability to be, something else. They have to be something like bromine, okay? Well, that is our solution. We are going to take alcohols, initially react them with something that turns them into an OG, and then go out and do a reaction that will, or go out and do just a reaction we did in 8A, right? Those reactions, those SN and E reactions that we just were not accessible to us as an alcohol. Okay, and that is the basis of every single alcohol reaction we're going to look at today. Okay, so whether it is a substitution, whether it's an elimination, and whether it is an oxidation, something that's new to alcohols, but we will also go over. Every single alcohol reaction in this class is going to involve turning OH into something else that is better as a leaving group, similar to bromine, right? And then that similar to bromine leaving group will facilitate all the reactions we did in 8A. Okay, so this is why it was so important to learn about bromides back in 8A, is because we were like, hey, appreciate how good these guys are, right? Because when we move to other systems, we're going to beg and wish that they were them. Well, actually, we'll just turn them into them, right? And we will base everything that we learned on the bromide system onto the alcohols and see where that takes us. Okay, so what is this G, right? What is this thing that alcohols are going to turn into? Well, it turns out alcohols have electrons. So they're really good, okay, not really good nucleophiles. I won't say that's a lie. But their electron pairs are somewhat nucleophilic, right? And so if I wanted to turn, G into a electrophile, I could turn to G plus. Well, hey, what's a very good plus electrophile that we used maybe in alkenes, right? What did alkenes that were also somewhat okay nucleophiles, what did we attack with them? Protons, the smallest thing in the world, right? Give something a proton and it suddenly changes its whole identity. Okay, so protonation, so using acid is what's going to make our alcohols activated as better leaving groups like a bromine. Okay, so acid additions, H plus additions. Okay, so I have my alcohol, and what I'm going to do is add H plus. Now, there's a lot of ways you can add H plus. I will just generically add as H plus right now. And then we'll see what those things could have been. Okay, but I'll just go ahead and add H plus. Okay, what do we make? Make OH2 plus. Now, a couple things that help out here. In terms of OH and OH2 plus, right? OH2 plus conjugate acid, incredibly activated. This oxygen has a positive charge on it. Remember, oxygen's electronegative, right? If you give an electronegative atom a positive charge, that is basically giving it a migraine. You're giving it a migraine. This oxygen, incredibly upset, very, very sad. It is, stressed out. Why do I have a positive, right? Why do I have a positive? It wants to get rid of that positive. So one way that you help out these reactions is you incredibly increase the dipole on that CO bond, right? It was there present, right? But now it's even more present, right? Because now you've increased the demand of electrons on oxygen. It's crazy pulling on those electrons now. Okay, so you've increased the polarity of that CO bond, making it more, more able to be attacked, more likely to be attacked. You've also changed the leaving group, because before, when I had a leaving group, all I did was I cut here and I said OH minus, right? Now when I cut here, what I have is OH2 or water, right? Hey, we just talked about this, right? Alcohols are kind of like organic water, and look at that, you just pull the water out of one, right? Just put a little bit of acid in it. Water is insanely better leaving group than OH minuses, right? This is like 15. Water is around, it depends on who you talk to, it's like 0, -1, but it's a non-positive number, right? The point is that Br minus is insanely good, right? It's like -8. So it's the best. It's the best. In the 8B world, it is the best thing you could ever have. Sorry, -8. Wait, did I draw my negative wrong? Oh no, I didn't. Okay. Anyways, -8. Water, almost there. It's kind of tiptoeing 0, -1. It is better than a positive number. So it is a way better leaving group than OH was better before. So those two things in conjunction are going to help us, because when we throw in, let's say, something that is a weak base, right? You guys might remember our weak bases being like halides. Like, for example, let's say what we had was here, maybe the identity of this was HBr, right? Now what we have is Br minus in solution. And now that weak base can facilitate a substitution. Now, this is where we kind of have to remember our reactions. Remember, substitutions switch the leaving group with our nucleophile. So we'll switch with bromine here. Okay. But remember, there are two types of substitutions, right? There is SN2 and there's SN1. The most important thing to remember as of just right now is that SN2 was very good on primary carbons because of less steric hindrance. So I'll just put, let's not use that. Looks like shipping and handling to me. Less steric hindrance, let's put that, okay? So less steric hindrance, and then SN1, right, was really good for, I guess it depends actually, because I know you guys heard different things. I will tell you what you need to know for this class. SN1 was really good for secondaries and tertiaries because of carbocation formation, right? That was the key hallmark of this reaction, right? We had carbocation stability. Okay. So if I'm using an acid whose conjugate base is a weak base nucleophile, like, HBr is a good example, HI is a good example, HCl is a kind of okay example, probably acceptable for the class, right? We will get an SN type reaction. We'll get a substitution. Okay. Now, again, because this carbon is primary, right, can't have a carbocation formation there, right? And we kind of already established that a primary is really good for SN2. So we know that for a primary alcohol, we're going to get really good SN2 reaction. Okay, so this is going to be an SN2. Okay, so OH to Br can change that very easily just with HBr, right? SN2 reaction. Okay. Maybe what I do then is, hey, I have an alcohol that's secondary and I do the same reaction. So let's do an HBr reaction like that. Again, first step is we're going to protonate. Okay. And again, I know this part is going to be a little iffy because there's a bit of like incongruence between professors, especially because you guys took someone last quarter who said that this doesn't necessarily work. It will work in this class, but secondary centers are very good at forming cations. So, or they're maybe not very good. Maybe in context of you guys, they're okay at it. But they're enough so that if we were to, form this oxonium or this water molecule, they can go ahead and leave and we can form a cation. And so this follows more SN1 type character, right? SN1 mechanics. Now Br minus goes ahead and attacks there. Okay, so we get that. Very common question I get is how do we know this, right? Why does it work? Well, luckily for you guys, I mean, 100 years ago, someone just did these reactions for us, right? They did it and they took the experimental data and they told us what happens. Just turns out that when you're in a very acidic condition, right? Very, very acidic condition, cations tend to thrive. So one little trick that I use that really helps me out a lot is I say H plus equals C plus. If I see an H plus, right, like an H plus condition, a proton condition, I'm looking to see if I can form a cation somehow, because cations tend to thrive in acidic conditions. Okay, a lot of reasons why. Usually the biggest reason is that there is solvent stabilization of the cation. Okay, this cation can be stabilized by local solvent, or local anything, just kind of stabilizing a little bit, some kind of a lone pair stabilization usually. Maybe another way you can think about it is that if we look at the leaving group, they're cationic, right? Solvent can also kind of stabilize the leaving group and help it leave a little bit faster. Whatever you have to use, just use it. The thing that I like to sort of remind people of is if CH plus, just think C plus. Right. If you can form a cation, you should. Okay, you should form a cation. Okay. So alcohol reactions, again, if it's primary, it's going to have to be some kind of SN2, because if I think about this carbon here, trying to form a cation, that's not going to work. So it doesn't work out, right? It's something we have to deal with. But if I am secondary in this class, or we can all agree on this, right? If I'm tertiary, if I'm a tertiary alcohol and I'm in like HBr, right? I am not at all am I doubting that this will leave to form a cation, right? And then Br minus just adds in. Okay, not at all surprised at that. Okay, this is also equivalent. Let's say you're just predicting product. This is also the same thing, right? So like if you're doing a predictive product, it's not necessarily a mechanism. I just like drawing out mechanisms because the more you see it, the better you get at it, the faster you get at it, and the easier it is to do. But if you're just predicting the product, right, these two are the same. You just, again, substitution, right? You're switching OH and Br. Okay. So substitution reactions, right? We can take an alcohol of any kind, right, and use something known as HX. So a term you've probably seen is nucleophilic acid. Nucleophilic acid just means that this part, the conjugate base, is a nucleophile. Right. That will substitute OH into an X group. Okay, so that's the first way that we can think about these. And again, usual suspects for these are going to be HCl, HBr, HI. Okay, usual suspects. Okay, again, if it's primary, think of more of an SN2 type reaction. So if you see a primary alcohol, don't doubt yourself. You see a primary alcohol, you see a reaction like this, instantly just go, do the reaction, right? Or do the substitution to switch OH into X, right? Don't really doubt yourself on that. Where things get a little trickier, right, is with the secondaries and the tertiary, or really with the secondaries, right? Let's say that I have this secondary here, right? And actually, let me go ahead and do this. Maybe you can think about why I did that for a second. Okay. So you have HX. Again, let's just think about this mechanistically. Mechanism can answer usually 90% of questions. So if you're ever stuck, and maybe you don't have access to someone helping you, maybe I'm busy or something, or maybe no one is responding to your question, usually you can go to mechanism and see what mechanism tells you. It can usually answer your question. But when I form this cation here, right? Obviously this cation, again, in this class, we'll assume that we will assume that secondary can form. Br minus can go ahead and add. And so this addition here can seem a bit like ordinary, right? It can seem a bit fine. But when I look at the starting material, remember, look at that carbon that I drew a wedge on, right? We had a name for a carbon like that. When carbon has 4 different groups on it, especially with specified stereochemistry, that's a chiral carbon. So that means that this starting material started off very specific, right? It specifically started off as the wedge variant of this molecule, which is different from the dash variant, right? You might remember RNS to kind of like name exactly which one it is. This would be the R-butanol, right? This would be the R-butanol molecule. When I finish this reaction, right, all I've really done is switch OH with Br, right? That's what I've done here. So the chiral carbon is still there. This carbon is still chiral. But the question is, do I also end off with the wedge variant? Or maybe something in this reaction makes it the dash variant, right? This is something we have to be able to solve, right? Something we should know the answer to. And so if you want to, you can pause and think about it, maybe even look back at your notes, but there is a very good, there is a very good answer to this. And there's something you'll want to remember. Whenever you're doing an SN1 reaction or any reaction with a cationic intermediate, if your final product is a stereoisomer, right, it has the ability to be R or S, dash or wedge, right, you will form both. You will form both of them, okay? This is just a feature of cationic reactions, right? The cationic orbital, it's an empty p orbital, so the nucleophile either attacks from the top or the bottom, right? If you want to think about it in terms of like in the plane, out of the plane, right? Either you attack in the plane, or sorry, like behind the plane or in front of the plane, right? Doesn't matter. Wedge face, dash face. The point is that when you have a cation, it's flat and it can be attacked from either side, right? So in this class, if you are forming a chiral center via HBr, HI, and you're doing substitution, right? You want to form both isomers. So you want to draw both, right? You want credit for both the answers. Okay, so just be mindful of that. That also means being mindful of other stereocenters too. So this should look sort of familiar. This here, change it a little bit. But let's say that I had this here, right? Again, oh, sorry, I drew the end answer. But let's say I had this alcohol here and I'm doing, let's say HI, right? And you can go through this mechanistically if you'd like to. I'm just going to save a little bit more time. But if I just sort of drew the addition with the I here, again, this I is going to be on a chiral center, right? We're going to want both answers here. You're going to want both the wedge and the dash. One cool thing to know here is that this center here always stays the same. This center here always stays the same. We did no reaction on it. If you do no reaction on a center, it really shouldn't change. So that center is just kind of a spectator center. It's sort of like a scary center, right? Throw on a chiral center to kind of to trip you out, but nothing to worry about here, right? We know for a fact that when this adds on, right, well, this will form the cation on the center here, and nothing else will happen. Okay, cool. So in terms of stereocenters, if you're doing an HX reaction substitution, right, and it's SN1, so it's on a secondary, tertiary as well, right? I guess you can imagine, let's say that you had something like this, right? That's a tertiary center with 3 different groups on it. This will also do the same thing when you add the bromine on, or iodide or chloride or whatever, right? You'll get both this and you'll get this here. Right, so you get both possible answers. So it's also applicable to tertiaries as well. I just realized right now I didn't really draw an example of that. So that's also possible. Okay. Actually, let's take this example. I'm gonna do something else to it too. So I'm gonna take that example. Now it was over here, right? But now what I'm gonna do is I'm gonna take that and I'm gonna move it right over here. Okay, I'm gonna move it right over there. Maybe I'll make it a bit simpler. I'll just make it a methyl. Okay, and we'll do the same reaction again. So HX. So I'm gonna skip a step here. I'll skip the protonation. We're gonna get the guy to leave, right? Because it's secondary center. Okay. Now, if you're just thinking about how this reaction would proceed normally, right, we might say that, hey, bromide just adds here, and again, it's on a chiral center, so both dash and wedge. It turns out this is not the final product. Turns out that actually our final product is going to be this here. Now, what in the world happened there, right? The bromine I mean, the cation, the bromine added, the cation should, if the bromine added on the cation, it should be on this carbon here, the secondary. But now it's over here on this tertiary carbon. What in the world is going on? Again, if you want to pause and look at your notes and figure it out on your own, you can do that. But I'll just remind you, right? Carbocations are very good at rearranging, right? Especially if you have one of the following two motifs. So two motifs that are really useful in remembering. Okay, a secondary cation next to a tertiary center, or a secondary cation next to a quaternary center. Okay, so I'll put the cation in red, and then I'll kind of highlight one of these groups just to show you guys. But these are our shifts, our possible shifts. Okay, our first shift will be H and the cation switch places. So we'll have the H here now and the cation here. You can erase the H if you want to. So you can go ahead and do that, and you can see where it goes, right? I'll just keep it in just so you can see how that, you know, it's really just like they're swapping places. I think that's the best way to visualize it. Same thing here, right? Methyl and H plus are going, sorry, not H plus, methyl and plus are going to switch places here. So plus goes here, and then methyl goes here. So carbocation rearrangements are possible, and they are the reason why I'm going to give you this next piece of information or next piece of advice. Anytime you're doing a predictive products problem on your exam, or anything that's not mechanism. So let's say you're doing just a problem like this one, right? And you're given like, you know, like HBr, and you're just said, draw the product. I always recommend, if it is a ionizable or if it's a cationic, like something that you can turn to a carbocation, please just draw the carbocation intermediate. Because looking at this, you might just see this and think, okay, OHBr, you know, Jim told me that's a substitution, so I'm just going to put Br and OH. I would be, you know, pretty happy that you remember that I said that. I would be a little sad though, because if you also remember this piece of advice, you'd avoid making this mistake, right? Because with this piece of advice, if you draw the cation just on the side of your paper, just draw the cation really quickly, you'll notice this follows the motif, right? It is a secondary cation next to a quaternary center, right? Or some kind of branching center, if you want to remember that. Secondary cation next to some kind of branching center, right? That motif will save you, and you'll see, oh, ha, let me just highlight this, or let me just mark this, right? That's a methyl, that's a cation. These guys are going to switch places. And what I'm actually going to get is this tertiary cation, right? Which is a much more stable cation than the secondary. And now I'm going to get my HBr capture on that, right? And so now, I mean, this is a regiochemical nightmare, because there are now two chiral centers. You don't know where everything is going. It's kind of, this is kind of a hard one actually, but the point here is just the concept, right? The concept. Cations like to rearrange, especially if it means going towards a thermodynamic sink. This is one of them. Okay. So I'd also want to show you guys another one, because there is a harder variant of this problem that you could experience. And it's never an issue to just know, you know, harder problems, right? So let's say you have this one. So I would say, you know, based on what we just talked about, maybe you have a good idea what's going on here. Maybe pause and try this on your own. But let's just go through some mechanism, right? Again, mechanism will answer 90% of problems, right? So I go ahead and I protonate, right? There's a bond here that breaks. I always kind of just imply that, but I would show it out that time. And then again, this carbon here is secondary, so I know it's going to do my rearrangement, or shoot, I didn't mean to say that. I know it's going to do my leaving. That's what I meant to say. And we form a cation here. So maybe if I just given you this problem with no context, you might think, okay, let's say that X is whatever, right? X is like Br or something. Obviously, then like Br can just add there, and maybe you can assess, okay, right? Is this a chiral center? Yes, it is. So being dash and wedge is going to be an issue, so I need both, right? That's a possibility. But with the context I've just given you, right, that cations like to rearrange towards more stable positions, maybe we might want to think about what's more stable here. Now, if I look at where this cation is and I look to the right, I mean, no one's thinking of going to the right, right? Because that's primary. And the number one rule we just talked about earlier was that primary cations don't exist. That's why primary alcohols, they don't tend to rearrange, right? They just tend to do your SN2, E2 reactions, no cation whatsoever, right? Prime alcohols just do their substitution as is. Okay, so those guys are usually pretty cool. So maybe we want to move over here. Now, a lot of you might be thinking, oh, I think he forgot to draw methylene. I think that's what he messed up on. And, kudos to you, right? It's good that you're thinking that, because it means that you're thinking about what carbocation stability, what, lends to it, right? It's, secondary, or sorry, tertiary is better than secondary. But let's look at this. Let's look at this for a second. Right. So again, I'll just go ahead and draw these out so we can kind of see how they change. They just kind of switch places. Okay. I'll get rid of the H here though. But let's look at this cation for a second. Why might this cation be a bit more stable than this cation here? Okay, this is a bit of a difficult question because this is right at the end of not 118. This is right at the end of 8, right? The answer to this question. Why this might be a little bit better. Okay. Starts with an R. Ends with an resonance. Okay. Now this is something, again, talk very briefly about this at the end of 8a. Remember that resonance can help stabilize these unstable intermediates, especially cations. And the best way to tell that resonance is happening, maybe it's a little bit hard to tell the way I drew it, but maybe if I drew it this, it would be easier, right? Anytime you have a pi bond next to a cation, that cation can resonate. And resonance is always a cation's best friend, okay? So this could be a tricky problem that could be like a mechanism problem, right? Where she asks you to show you the mechanism of formation of a product, right? I don't remember if she shows you the product or she makes you draw the product and then do the mechanism, but something worth considering, right? Again, that's why I always recommend just draw the cation out. You never know when it can save you, right? Maybe on your quiz you get something like this, right? I mean, the whole point of this is you have some alcohol and that motif, right? You have that motif available to you, right? That motif of having that branching center next to your secondary alcohol, right? Drawing that cation just helps you out, helps you see it, right? Like, oh, okay, that's going to shift over. Oh, I realize I've not been drawing the shift arrows. My bad. The shift arrows are always that the bond of the shifting thing is going to attack the cation. The cation, sorry. I apologize. I forgot to draw those in. So that's how we can initiate that attack there. And again, it's just like it's trading places, right? Methyl switches with the cation. And now we have something to capture that BR with. Okay. So look out for those rearrangements. I imagine that I think on the practice quiz, it was like 5 or 6 predictive products, right? Maybe one of those on Monday will be a rearranged one, right? If not that, then the mechanism, right? Because like those are the 2 places where you can really test that out. Okay. Now, one last thing. This is something I would study very last minute. This is not something I would waste too much brain power on. There is one niche example of a shift that we do tend to see. It's very specific though, so if you wanted to memorize this exact example, you could. This here is a 5-carbon chain, but it's kind of drawn in a weird way. It kind of looks like a cross in a sense. I mean, maybe I should make it look very much like a cross. That's the best way to recognize it. This is the neopentyl alcohol. We call it neopentyl. Maybe you can think of it as like the Jesus alcohol or something. I don't know. It has a cross in it, whatever you have to use. But this alcohol here can do some really weird things. Let's say I did an HX reaction. When you protonate this, right, it is primary, so it doesn't form a cation, but it is next to a very branched center. And it turns out that this very branched center can actually rearrange. So we can actually maybe I should push not this middle methyl, and maybe you'll see in a second why. I do that because then we can retain this part, but that OH is going to get replaced by that methyl there, right? And then this here is just going to become a cation. Okay. So again, kind of a confusing rearrangement, but this is very specific to this, so you can kind of remember it. X minus being a nucleophilic acid can just go ahead and add on, right? And what we get out is this molecule. Okay, so very, very specific rearrangement. Something that I would just ask you guys to memorize. Don't really worry about it too much. Again, the main motifs we're looking for rearrangements is these secondary alcohols next to these branching centers. These are the main motifs, and there's many ways you can hide them in, right? Like I think rings are maybe one of the hardest things to see them in because they're not like drawn specifically like this, right? They're a little bit hidden, but again, just looking for that. If you draw that cation out, secondary cation, hey, tertiary center, I'm not hesitating, that's going to rearrange. right? So look out for these motifs, okay? So a lot of information, but let's just quickly summarize it on this page here, right? Alcohol substitutions are possible. We just got to do them in acid, okay? And so if I do, if I wanted to do a reaction with a primary alcohol, right? Something like a ethanol, pentanol, butanol, something normal, linear, right? I just do HX, simple SN2 reaction. I just replace O with X, right? I don't have to think about this at all, right? I'm just replacing it, simple SN2. Okay, and so you can get pretty creative with these. Maybe I even throw in this example here, but I throw the alcohol all the way down here, right? Again, no branching, no neopentyl branching here, so I don't have to really worry about rearrangement, but it is a primary alcohol. So I know it's going to be SN2 like. So I'll get X there, okay? Again, with the primaries, just keep in mind, right? If I have that neopentyl system, something that's just worth memorizing, I can get rearrangement. So this is what we would call a concerted shift. I'm just going to try to teach you guys as much vocab as you can, just because, you never know. I mean, there's a lot of vocab on your quizzes, so it's just, you may never know. I might just say the word that you need to know. So HX here, this is just a concerted shift. Again, this is a neopentyl. Call this a neopentyl alcohol. And yeah, so that's the primary alcohols. Secondary, tertiary, right? Those are going to be more SN1 like. So if I have a secondary, right? Oops, not that. Right? If I have a secondary, right? Obviously, this is just going to go through a cation. And then remember, if that cation, when it captured by a bromide, results in a chiral center, we want both possible answers. I just recommend drawing both, right? That's the easiest thing you can do. Right, just keep in mind, right, if you have the possibility of rearrangement, right? I know I'm drawing this in here just as like a placeholder. I just want to have, I guess I want the ability to draw two answers here, but just keep in mind, right, when I have the ability to rearrange, best way to see that is just draw the cation out really quickly. You see that motif, you know that the cation is going to move here. So when we have addition, we'll have addition of a bromide here. Oops, that's not going to do what I wanted to do. Oh man, so I have to move it. Oh, what if I move it here? Okay, that will do what I want to do. Okay, I'm just trying to make sure it ends up chiral, that's all. We'll make this, and we'll make this here. Okay, and again, any other chiral center on the molecule that's not participating in the reaction just stays the same. So that's what I want to exemplify, because I want to exemplify a shift and also exemplify, hey, we get two answers if there are two answers. Okay, cool. So HX reactions, really good at facilitating SN2s and SN1s on our alcohols. So, maybe on the way to the synthesis of a molecule, maybe I want to turn my OH into something like, for example, maybe I want to turn my OH into like a cyanide, right? Cyanide, that's a pretty good group. Problem is, though, is that there is, no way that NaCN, which is a weak base nucleophile, is going to substitute this. It's not going to work, right? OH is a bad leaving group. So maybe one thing we can say is, okay, I can just use H plus, or maybe some kind of acid version of ACN. That actually might be able to work here. I don't, this could be a possibility. What I will tell you, though, is that HCN is incredibly toxic. This will kill you. Okay. It smells like almonds, and I mean, I think it does. I don't know, because I haven't smelled this thing. I don't want to die. Okay. HCN is not going to be the best thing to propose, right? We want to be safe in the lab, right? So instead of just going straight into CN, right? Maybe we think, okay, maybe we don't go from OH to CN with HCN. Maybe we go from, NaCN with something that is a way better leaving group than alcohol, right? Something like a halide, maybe a bromide. Well, hey, alcohols can be turned to bromides with HBr, right? So this is going to be a common theme what we'll see in syntheses of these molecules. I don't know if you have to do synthesis. I'm just in case you have to, I'm just like telling you guys, right? This is sort of the utility of this substitution, right? Turning OH into these halides, and I'll just again make it generic to X, which X usually is Cl, Br, and I. right? These reactions are going to allow us to access our alkyl bromides that just did other reactions before. So in the lab, how you might see this replicated is you might have, maybe you have an alcohol functionality and you might try to do a reaction straight up from the alcohol. For example, maybe, I don't know, maybe there is a safe way to do the CN reaction, right? Maybe I can form it in C2. If you guys know what that means, it means it's on site right when I need it, and I can try this way. And maybe for some molecules this works, some it doesn't. Maybe for me, I try this and it doesn't work. Well, it's okay, because if that doesn't work, then I'll just turn OH into a better leaving group, right? And the way that we've learned in this class is I just put HBr in, right? Turn this into a Br, and then I will do my reaction. Okay. Now, oops, sorry. Again, that will lose its stereochemistry. And then I do my CN reaction. Okay. So again, applying this reaction that we just learned, how can we apply it to real world situations, right? That's something we can do. Cool. All right. So those are our substitution reactions. So how do we do elimination reactions, right? Well, if I look at my substitution reaction, what made it work so well was that, hey, I took my alcohol and I reacted it with HX, where X was that nucleophilic component, right? X was a nucleophile. So it was something that is a good nucleophile. So I'll put here good. And as a base, it was bad, very, very bad, very, very bad. Okay, so that's what a nucleophilic acid does, right? Is it uses an X that is a good nucleophile and it's a very bad base. That's how we get the SN type reaction to work. So if I had an alcohol and again I wanted to do an E type reaction, right? I've got to use an X which with some Y, where Y is a bad nucleophile, very, very bad, but it at least relatively speaking, it is a good base. It would rather act as a base than ever act as a nucleophile. And there is a category of things that do this. We call these the non-nucleophilic acids, of which I would recommend you knowing 3 of them. Okay, those 3 are H2SO4, highly related H3PO4. They kind of look like each other, right? So that's not hard to remember. And then sometimes you'll see HF. Uh-oh, halogen. That makes us a little bit irked out. It's okay. I don't think you'll have to know HF, but I always include it just in case because it is something you should know. HF is a terrible, terrible, terrible nucleophilic acid. It is much better as a non-nucleophilic acid. Okay. So if I use a non-nucleophilic acid, something like these 3 here, I will see usually, I think the one you'll see the most is H2SO4. You will usually get out an elimination product. Okay. So how does this work? Well, H2SO4 again is acid, so we'll break the bond between H and HSO4. I'm just not showing it to make our water. And again, this is a primary alcohol, so should I be making a cation? 2 seconds. Should I be making a cation? Not at all. So we're just going to do our elimination reaction straight up, right? So this is E2. A good way to remember how to do eliminations is that the group that holds OH2 plus, we call it alpha. Everything attached to alpha is what we call beta, and it is from the beta carbon that we take a hydrogen from. So we take the proton from there, okay? And so what we get out is an alpha beta double bond. So if you have issues drawing out alkene products, maybe try using this nomenclature, alpha beta nomenclature, to help you figure out where to draw your double bonds. Okay, so at least for primary alcohols, you're just drawing an alkene where the alcohol was. So let's say, for example, I have this alcohol here, right? And I have H2SO4, right? Usually very, very hot, very heated, right? I will just, in the stead of the alcohol, draw an alkene. Now, you might have seen me make a little bit of almost make a mistake there, and I imagine some of you will do this too. It's very tempting to do that. Keep in mind that we're making a carbon-carbon double bond that already exists, right? This started off as 1, 2, 3, 4 carbons. This has 1, 2, 3, 4, 5. I imagine Liebens has some partial credit associated to if you accidentally add a carbon. But, just quickly do some numbering for the alkene ones, because, I mean, you guys almost saw it too, right? I drew this initially. I make mistakes all the time too. What's really important, though, is that we catch them and we find a way to solve them, right? How can we make sure we don't make them again? right? Better to make mistakes now than later, but how do we solve so that we don't make those mistakes later? Okay, that's one way you can do it. Just count carbons. 1, 2, 3, 4. 1, 2, 3, 4. It should feel short to you. It should feel short, right? It should feel like you drew something wrong. Counting carbons should work out there. Okay, so primary alcohols, pretty simple. They're just gonna lose out water. Usually you just, again, just take from here, right? Move it out. So nothing too crazy there. Okay. If I have a secondary alcohol though, again, we're going to make water. And what's that water going to want to do that it's on a secondary carbon? This is a question I'm going to ask all quarter long. Okay, we're going to see this so much actually. This question being asked and the implications of this question. You make water on a center that can form a cation, that cation is going to form. You make water, it's going to leave. Okay, it's going to leave. So we're going to ask this question maybe 100, 200 more times. You make water, it's going to want to leave. And that's what it's going to do in this case. And so again, right, we're going to get a removal of the proton. I realize I didn't show here what took the proton. I'll show it here this time. Actually, let me be a bit more careful. I always kind of forget, even with the higher classes too, that you guys are just learning this. So I should be drawing out everything. So my bad, I will draw everything. So draw out that or let's draw this one better. Really, it should be this. There we go. Okay, so giving off the H to the HSO4, right, losing water, and then an HSO4 minus, right, is going to pull off a proton. Now, again, like I mentioned, right, the carbon that holds the alcohol or the water is what we call alpha. In that case, it's the carbon that's the cation. Everything attached is beta, right? So not only is this carbon beta, but also this carbon is beta. So if eliminations are just beta eliminations, I mean, that's where we're taking the H from, then you can imagine that there are two alkene products here, right? There is one alkene product where we eliminate on the left side, so between this alpha and this beta. There's also an alkene product where we eliminate on the right side, so this alkene beta. Okay, either one is possible. Okay, so the question is there going to be a difference in product distribution, or both of these 50-50 and I should draw both of them? Well, here's where it's nice to know, really good rule of thumb. When it comes to alcohol dehydrations into alkenes, you always want to make what we call the Zaitsev alkene. Zaitsev is always the more substituted alkene. Okay, more sub. Another way to think about this, if you're doing a mechanism and you're trying to solve for the arrows, is to eliminate on the beta that is more substituted. So I'll call this HZ because that is our Zaitsev position. Okay, HSO4 minus takes that proton, right? Shifts those electrons in between the alpha and beta carbons. So this is alpha, this is beta, and we get our alpha beta double bond. Okay. Now, if you're really worried, you could draw all alkenes and just circle the one that's major if you wanted to. Liebens does accept that, I think. I think she does. You should ask. I think she accepts it where you can draw an alpha beta, or you can draw like the major and minors as long as you label them. I think that you should just draw the major, right? Just draw the major Zaitsev and you'll be fine. Okay. Should work out. Shouldn't be too much of an issue. Okay. Cool. So we can see a lot of applications of this principle, right? For example, we can see it here. Again, let's draw out our arrows showing all of them. So alcohol attacks the proton, makes OH2 plus, and then this is going to leave us a cation. Okay, and then again, I can ask myself, do I want to take the beta that's on the left or the beta that's on the right? Again, carbon that holds the cation is alpha, so these two carbons here are beta because they're attached to the alpha carbon. So which hydrogen do I want to take? Again, according to Zaitsev's rule, I want to take this guy here, right? So arrows are going to look like this, boom, boom. And what I get out is this alkene here. Okay, this alkene here. Now, I want you guys to look at this alkene for a second and maybe consider that this alkene might have another isomeric form. Okay. Now, this is a bit of an advanced question, so I don't think you might not get, maybe she might modify this so that you don't get something like this, but it's still something good to think about. Okay. Let's say you get this trisub-alkene like this. There is another form of this alkene. It's if I, took this alkene, but then I moved the methyl on the right side, I moved it down to make this alkene. Maybe you guys remember back in 8A, we had a name for these two different isomeric alkenes. One we called E and the other we called Z, right? Maybe take a second to think about which one is better, or sorry, which one is which. So first figure out which one is which one is E, which one is Z, okay? Remember, by priority rules, on the left side, the ethyl is bigger. On the right side, the methyl is bigger. So wherever those guys are in space are going to determine E and Z. Z we can remember by same side, and then E we can remember by opposite side, I guess. I don't know, opposite, whatever you want to remember. It's just the opposite of Z, I guess. So it's like more of the trans and Z is more of the cis. But this is E and Z. When it comes to alcohol dehydrations, we might want to know which one is better for an advanced problem like this one. So which one might be better? Which alkene would be more comfortable drawing? Well, first off, actually, I would say this. If you're not comfortable with knowing which one's better, just draw both, right? And then you can make the argument that, you know, it wasn't clarified ever in lecture or whatever that which one to know. But I think we can still prove to ourselves which is better, right? Which one might be more stable? When substitution is the same, right? I mean, obviously up here it wasn't the same. This was more sub, this was less sub. But when substitution is the same, we rely on sterics. So ethyl being very, very big, and methyl just, you know, being kind of big, but, you know, doesn't want to hang out with ethyl. This guy here is going to experience a little more steric hindrance than this guy is over here, right? So generally, if you have to choose between an E and a Z isomer, you want to choose the E isomer as your major. Now, if you're worried about this kind of concept, you're like, oh my God, that you just said words that I think I heard 10 years ago. They are foreign, it's different language to me. That's totally fine. That's totally fine that you feel that way. I would just draw both. Just draw both. Worst case scenario, she takes away a point, right? Best case scenario, she realizes, oh, she never clarified it. I don't know if this will clarify it or not, but it is something that comes to my mind that you should know. Okay, cool. So, advanced problem, right? If we have the possibility of making a stable alkene, but one is E and one is Z, maybe I lean more towards the E one, right? Minimize those steric conditions. So, less steric. If she did go over this in class, then this could be a great vocab question, great general knowledge question, right? We prefer the E in Zaitsev alkenes because, hey, they are less steric. Cool. Now, one thing we don't have to really care about with the alkenes is stereochemistry. So remember back here, we really had to take very good care of, you know, when I lose this stereocenter, what happens, right? I get two stereocenters because of SN1 mechanics. But E1 doesn't really care about that because it's an alkene, it's flat, right? So just make sure you don't mess with anything like any other, like maybe you might have an example where you have like a center here. Like let's say we have this here, right? And you dehydrate that, would just be real quick on this one, right? You form the alkene there. Other side is just the same because these are both the same beta, right? Don't really have to care about the stereocenter that the alcohol was on. Just, you know, be mindful of the stereocenter that you had before, right? Don't change it. This is a wedge, by the way. I don't know if that's obvious or not. That's a wedge. Just be mindful of that. Don't lose that. But we do have to care about, so stereochemistry, nothing to care about, but we do have to care about rearrangements sometimes. Okay, which actually maybe some of you, maybe something was dinging because you're like, oh man, I got him. This guy is not as smart as he thinks he is because he didn't do the one thing that he was making a big deal out of last time, right? Cations can still rearrange, right? I mean, it's still H2SO4, but you know, maybe it's not so necessary. So when I look at an example like this one, so let's draw this one. So this one goes to this cation here, right? There is a huge possibility that this H actually just internally rearranges, right? Yeah, that's totally possible. That is totally possible. That hydrogen can totally internally rearrange. And then maybe we can do some kind of, you know, elimination reaction. Right now we have sort of three betas to concern ourselves with, right? We have this one, and this one. And so of those three, right, I mean, two of these are the same. These two are the same. You can convince yourself because these are ethyls. So they have to be the same. So it doesn't really matter which one you choose, but, you know, you can still make that same alkene. Okay. So cations can definitely rearrange in these alkene reactions. It's just that sometimes maybe it doesn't matter. Because yeah, this does rearrange, but this doesn't really change much than if I just did the elimination from here, right? Like if I just do the elimination from there, that gives me the same product, doesn't it? It's totally possible. So I would say that for alkene reactions, if if you're not sure when to rearrange and when not to, just always rearrange. Who cares? Can't be wrong. As long as you get to the right product, that's totally fine, right? In this case, you didn't really have to rearrange. And you would still get to the same product that you would have if you had rearranged. Doesn't really matter. But maybe we can modify this example to an example where it might matter, right? Maybe I can make this a little more complex, right? So I can turn it into this and then say, okay, what happens when I draw the cation? So actually, you know what? Just to save some time, I'm going to draw the cation already here. So if you want on your paper, you can pause and take a second, draw the mechanistic arrows we've been doing to get from here to here. But for sake of time, I'm just going to skip that part. We'll get to this part here. Okay. Okay. And then we'll rearrange this. So let's say we rearrange this cation. Okay. Now when I consider my betas, right, this, and this, totally different ballpark, right? Now all three of these are different. So this is a, no sub. This is I guess, primary. This is secondary. This is tertiary. Now the betas do matter a little bit. And also the fact that, hey, this guy is the best. And we wouldn't have known that until we rearranged. Okay. So definitely we can form this alkene here, right? Between this alpha and this beta. That's the alkene that we would want. Right. And then again, we can ask that advanced question, right? Of, hey, this looks like it looks like a Z alkene. Maybe there's also an E variant of it that's a little bit better, and I would probably want to choose that one. So advanced problem. I would reckon that if you get asked a question like this, it's one question or it's an easier variant. But again, the more you think about these harder ones, the better you'll be at the easier one, because you'll be like, oh my God, I spent all that time in Jim's video, like trying to rack my mind around these, hard problems. What am I going to do on the quiz? And you go on the quiz, you're like, oh my God, this is literally breakfast, right? This is literally breakfast. I could have done this in 2 minutes. Why did I get 20? Right? Cool. So rearrangements, what's the final verdict? Do them, just do them, whatever, just do them. It might, at worst case scenario, you added an extra step to your mechanism, but you still got the right product. Best case scenario, you see a rearrangement you weren't going to see if you didn't draw the cation and the shift. Okay, so it can't hurt to do it. Can't hurt to do it, really. Okay, where rearrangements are really going to matter are going to be when they are of quaternary centers. Because let's say that I did this reaction here. Actually, just to expose you guys to different acids, let me do H3PO4. Right, that's not a bad one. Right, in the heat element. Right, drawing out this cation might indicate to me, oh yeah, I'm going to get a rearrangement. Right, this guy is going to move there. And what I get out is this here. And then again, when I look at all of my betas here, so here, here, and here, right? Now I see this new interesting beta that gives me this really nice stable alkene. Okay. So this could be a good example of where rearrangement is really nice to see. I mean, hopefully all in all, you guys are just convinced by when I say, if you have the ability to draw a cation or have a cation formation, just draw it and see where it takes you. It might just illuminate some new pathway or show you that that product was actually not as simple as it might have been, right? As far as I'm concerned, there really isn't any, I mean, I guess you could do a neopentyl. I guess you could, right? I mean, this just requires memorization though, right? Memorize and neopentyl rearranges into this. Right, and then this makes this alkene here. Neither E or Z, so who cares, right? So, yeah, cool. Now, one last thing that I'll bug you guys about with these alcohols before we go on to, the last set of reactions, I believe, for alcohol, is this delta. I've been kind of using delta, right? I've just been saying, okay, I guess I actually haven't been at all doing anything, so I apologize. I've been kind of speeding through this a little bit. Oh, this is a blank page. Anyways, oh, I should have been drawing deltas here. That's really bad of me not to do that. Okay. But this delta, what does it mean? Some of you guys might know. Delta just usually means temperature. it means a lot of heat. But what does that mean in the context of an elimination, right? Well, it turns out that H2SO4 can be a little bit finicky. Okay, so what do I mean by that? Well, it is very, very useful for us when we do an H2SO4 reaction, right? And let's not even draw the delta, right? Let's just kind of go through this very quickly. But it is very useful to us that we have a non-nucleophile in solution, like a non-nucleophilic acid in solution, because we're trying to limit the amount of SN type reaction, right? So if we take the acid out of the equation, then nothing to worry about. Well, it turns out that alcohols also like to be nucleophiles. So it turns out that this alcohol here can also, the same way that this alcohol attacked a proton, this alcohol can attack one of its brothers, right? And kick off that water molecule right there. And so what this ends up leading to are these, sorry, did I do that? 1, 2, 3, 1, 2, 3. There you go. Ends up leading to the formation of these symmetric alcohols. Or sorry, symmetric ethers is what I meant to say. Okay. So we can also make ethers in H2SO4 or H3PO4, right? At low temperatures, it is pretty significant that you'll see these symmetric ethers start to emerge. Usually you'll see these with, primary alcohol, so like an ethanol. You can imagine on industry scale, this would be a pretty easy reaction to do, right? Turn this into this. And then what we get out is this here. Again, primary center, so it's going to be more of like an SN2 type reaction type thing. And then what we get out is a symmetric ether. So we can make these symmetric ethers fairly easily using this reaction. Okay. Secondary tertiaries also work. Like it's not like they don't. So I can also use this. They just probably go through like I'll do this really quickly. They just probably go through a cation. But again, cation solution, I mean, shouldn't really surprise you that these guys can attack each other. Usually bulkier alcohols are not the best nucleophiles, but it isn't unheard of. The point is that if you have H2SO4 at a very low heat, you kind of run the risk of a lot of things happening. So you run the risk of making symmetric ethers. Maybe you do make some of the alkene product, right? It's a possibility. It's not the best thing in the world. So, I ran out of pages, so I have to go back to the beginning. It's kind of funny. Okay, whatever. So if I try to think of a solution for this, right? How can I, make sure that I only get elimination? One thing you can look at is the fact that in an elimination, right? What do I get out, right? I'm making an alkene, right? I'm making a water molecule. Okay. So I'm getting out like 2 molecules, right? That's getting out 2 molecules from this. If you look at a substitution though, right? 2 of these molecules are joining to become 1. So entropically, right? The substitution is favored. Or another way to say about this is that entropy wise, right? The elimination is a bit unfavorable. So if you think back to the delta G equation, which should be this, T delta S, right? Again, in terms of entropy, right, substitution is already a bit favored. This is where elimination is kind of lacking, right? This is where we kind of have to help out. Oh, wait a minute. Am I saying that wrong? No, sorry. You can see I'm no physical chemist. I'm no physical chemist. I always mess this up. I might even mess this up now. So I'll try to say this carefully. So when it comes to elimination versus substitution reactions, the entropy argument, where you have an increase of molecules for the elimination and a decrease of molecules for the substitution, it should be that the elimination is entropically favored. Right? Yes. Okay, sorry. I apologize. That should be better. I just had to, sometimes you just have to walk yourself through the statement. So this is an increase. I forget, this is an increase in molecules. This is a sort of decrease, I suppose, a decrease in molecules. The point is that this is increasing entropy. So this is increasing entropy or increasing S. So, okay, you know what? I butchered it, whatever. I'll just get to the point. The point is, if you have a process that is, increasing entropy, I mean, the best way to increase entropy is by the delta G equation, just increasing the temperature. Okay. So the general rule of thumb, I believe, I saw someone write this in the chat, 180. That's what you guys learned. 180 is your elimination temperature. And then anything below that is going to be substitution. Okay. So just memorize the 180 number. I think the other number, at least in 118, they learn is 140. That's the substitution number. So you can use that one as a general guideline. But 180 is the one you want to know for elimination. Okay. Sorry, made a mistake. Happens. I guess if you guys want to know, this is kind of what I was like really confused for a second. I was like here just scratching my head because I knew I had said something wrong. I just couldn't for a second figure out what it was. Okay. This is actually what I look like, by the way. I'm just a line drawing. I have dots for eyes and a little tiny nose, and then an anatomically correct ear. But other than that, not much going for me there. Okay, cool. Anyways, if you want to promote the elimination reaction, use high temperature, use 180. If you want to promote the substitution, just use a lower temperature. But usually the low temperature comes with a lot of mix, not usually the best reaction. Okay, so this reaction here, I know for a fact I'm getting the elimination. If I run the same one lower, maybe that 140 degrees that I said earlier, right, I'm probably going to get the symmetric ether. Okay. So let's actually just talk really quickly about the symmetric ether component. This is the only kind of ether that's really good and should be the only one that's asked on your quiz. If you're going to make an ether on the exam or sorry, on your quiz, then ask it's only really good to make symmetric. Because let's say that I had this alcohol, right? And I put them together at 140 degrees H2SO4. This is going to be a mess. Because first off, how do you know who's going to protonate, right, between these two? You don't really know. And how do you know who's going to attack, right? You don't even know that either. So to kind of very quickly summarize this, you're going to end up with symmetric ethers of both kind, and you're going to end up with the mixed ether or the asymmetric ether. So the question, maybe the question is, maybe you're thinking maybe this makes the asymmetric ether. It doesn't. It makes all three of these. Right. So this is the nightmare. This is a nightmare to separate. These are, separation requires that there's some significant difference. There is no significant difference between these three. You just made a layer of ethers. Congratulations, I guess. So very, very bad process, but symmetric ether wise is very good. Although there is one thing you can do that will make a pretty good symmetric ether. It's a very specific example. Okay. And that is the following. So I think you guys should try to think of a mechanism for this before we move on. But this at like 140 degrees will make a very good symmetric ether. Okay, this will make what we call tert-butyl methyl ether. So TBME, tert-butyl methyl ether. This will make a very good tert-butyl methyl ether, a mixed ether. And you might want to think about why that is. Why might that be the case? Okay, so maybe pause and think about that. So if we look at the obvious difference is that this is tertiary and this is primary. So maybe we have to think about what makes a tertiary carbon good or a primary carbon good, right? What do those things do very well? Well, one thing to remember is that tertiary carbons are really good at making cations. So when I protonate this tertiary alcohol, guess what? I get out a tertiary cation, and that is going to be very stable. So it is very likely that in this solution, you are generating, not very fast, but at a appreciable rate, a lot of tertiary cations. Now, you might remember I said this very briefly, but bulky alcohols are not very good nucleophiles. Well, that's okay, because in this solution, we have probably the least bulkiest alcohol possible. We have methanol. So methanol can act as a very good nucleophile onto the center. And what we get out is the tert-butyl methyl ether. Okay, so we're taking advantage of the fact that tert-butanol, very bulky, bad nucleophile, but good at making cations, and we're using methanol, a very bad cation generator. I mean, methyl cations are terrible, right? It's like a primary cation, very, very bad. But it is a better nucleophile than a terbutanol will be, so we can do a very good mixed ether. So another advanced question. A lot of advanced questions today, right? Don't feel too worried if these are like kind of hard, right? And they're advanced questions for the 8 level, or like hard to think about. Okay, cool. All right. So there is one way. That's one way you can make a symmetric ether. Sorry, asymmetric ether. But you cannot do it this way. This is not going to work. It's just terrible. Only this way will work. So is there a better way to do this, right? Is there a better way to make a symmetric ether? The answer is yes. Okay, but we have to do a different type of, a different type of approach for this kind of reaction. Okay, if the acid reaction doesn't work for this, then we want to use a different condition, and the only other condition is base. So you guys might remember we talked very briefly about the fact that, hey, if I put a strong base, like let's say an NaOH, in front of an alcohol, we're not going to get the elimination, right? Or the substitution. What we're actually going to get, because this is a strong base, we're going to get the acid base, right? Because remember, in terms of substitution, this is not going to work because alcohols are bad leaving groups, and there's no acid in base to turn this into a better one. And also, if I think about the E2, right? Hey, A2 is an acid base with a CH bond, but we have a very acidic OH bond. So that's the bond that's going to fly off first. So by taking off that, OH, we turn this into O minus. And O minus, again, not a very good leaving group, but it is a pretty good nucleophile. This is a pretty good nucleophile. And if I introduce to it some primary alkyl bromide, so some primary RX, so primary alkyl halide, what I will get out is the addition of the alkyl halide on the ether, or on that O minus, on that alkoxide, will form an ether. And so this is a reliable way to make asymmetric ethers. So I don't want to spend too much time on this because I imagine Levens is probably going to talk about this just right coming up. I'm just mentioning this just in case. I mean, it's a good segue. I mean, it kind of matches in with the material. So let's say that I had an ethanol, right? And you see a strong base. You can see a lot of things. You can see NaOH. So what are some bases that we can see? You can see NaOH, or you can see like NaH. That's a very popular one. I've used this with an alcohol before. It works wonders. You can also just see it with some kind of NaOR. So R is just any alkyl chain. You never know. Maybe she just uses the OR minus version of this. So maybe what you see is this here. So ethoxide. Point is the first step is some kind of base, and then the second step is some follow-up. Either the second step can be on the same arrow, or sometimes you'll see it on a separate arrow. So in this case, let me stack these on each other so you can see it can be any of these. Right? This will make O minus like that. And then the second step is some kind of alkyl bromide. So maybe what we make is something like this, right? You're just adding all of this onto this end of the ether. So it looks like it's 1, 2, 3, 4 carbons. So 1, 2, 3, 4. And on that third carbon, we just have a tail. And there you go. You made an asymmetric ether. Okay, cool. There's a name for this, by the way, if you need to know it, whether you need to know now or later. We call this Williamson. And Williamson ether synthesis has some pretty cool applications, specifically in that it is going to introduce a type of reaction that you see a lot in this class. So I'll show you one example now, but I'm pretty sure you won't see this until later on. But you can do something we call an intramolecular reaction. What that just means is that the OH and your nucleophile and your electrophile are on the same carbon, or sorry, on the same molecule. So let's say I add base to this, right? Form the O minus, right? Because that's just going to pull that off. And then instead of attacking, like let's say there's another one of these here, because maybe the thing might be, oh, maybe you might attack here, right? And you might get an ether like that. Instead of polymerizing like that, what will happen is that the O will actually attack internally. So this O minus will actually attack itself. So it's intra. So O is 1, and it attacks carbon 2 here, and then I count everything in between. So 1 attacks 2, 3, 4, 5. So this makes a 5-membered ring with oxygen in it, where you can choose to count like this, right? And so if there's like other things on here, like maybe there's a dimethyl at 3, to put that there. maybe there's a methyl at 4, to put that there kind of thing. This is, don't worry about this. Don't worry about this. I don't think this will show up until the second quiz at least, because you guys haven't even really talked about ethers yet. I'm just bringing this up because the question was, if we can make symmetric ethers, which you guys have learned, how can we make asymmetric? And there is one acid way, but really the base way is the way that we go. Okay, the base way is the way that we go. Cool. All right. So with that being said, that's the majority of our reactions. These are our reactions where we kind of functionalize the alcohol into an electrophile and do those bromide type reactions. Okay, so again, right, if I want to do some kind of substitution, right, use a nucleophilic acid, I will do SN. If I want to do some kind of, elimination type, 180 degrees with some sulfuric acid, that will give me my elimination type reaction. Okay, cool. So hopefully that last hour and a half kind of clarifies anything or kind of introduces something in a new light to you guys. If there's anything that's confusing, please let me know. I wouldn't be surprised. That was a lot of material for an hour and a half. Okay. So the last thing we're going to talk about today, maybe take 10, 15 minutes, round this out, is going to be something that alkyl bromides just can't do. Okay, so alkyl bromides, they can do E's, they can do SNs, that's pretty cool, but they cannot do oxidations. Alcohols, on the other hand, that's in the name, oxidation, oxygen, right? They're both ox, right? These guys can be oxidized. And so I guess the best way to kind of introduce this idea is to kind of show you guys what an oxidation is. So oxidation is when we take some kind of carbon unit, maybe this, and what we do is we replace the hydrogens on the carbon with some group that steals electrons from carbon. So it oxidizes the carbon. It takes away electrons from it, essentially. Okay. The most simple oxidation is turning one of those H's into an oxygen, right? Because that's the first level of polarity, is to add an oxygen like that. So we're left with these two hydrogens there. So alkane to alcohol, that is one level of oxidation. Another level of oxidation is to take away another pair of hydrogens. And one way you can think about it is to just add another alcohol here, just like that. That's something you can do. But this, as you'll learn later in the course, is actually a very hidden way of just saying this. We just take that O single bond and we turn it into an O double bond. Okay, so this is another level of oxidation. So this would be like the second oxidation state. Okay. Now there is one more hydrogen, so hey, maybe we just apply that concept again, or we just replace it with an OH, and this is our final level of oxidation. At least that retains, the molecule. This isn't actually the final level. You can actually oxidize this one more time, but that would actually require cleaving this bond here. So you can achieve total oxidation if you turn into CO2. But we won't see anything like that for a while. Mainly for these reactions we're going to learn is going to require us to just understand really these oxidations here. So alcohols, really carbon can be oxidized through the alcohol, and it has its own series of oxidations, right? These three that I have highlighted are the ones that are basically the most important. Those are the most important oxidations, okay? So again, if the function is of these three oxidations that we're losing these hydrogens, right, then our mechanism or our reaction is going to require pulling those off, okay? Now, usually you guys don't learn a mechanism for this, but I like to just show briefly one so that you understand it and you can see why it works. It always just helps to have a little bit of mechanistic understanding of things, right? But let's say, for example, I want to do this first level of oxidation. So this has a name, actually. This is called an aldehyde, okay? So alcohol to aldehyde, right? I want to facilitate this oxidation. There's quite a different things that can do it. But generically, if I'm thinking generically, how can I think about an oxidation of an alcohol? Very simple. Remember, every alcohol is a very bad, reactive group. So what do we always do? We always turn the alcohol into some group G. So all oxidation reactions, although you'll only learn one, I believe, in this class, like one group of them, all oxidations involve adding something to the oxygen, okay? And then from there, well, let's look at this. We're going from a C single bond O to a C double bond O. Formally, that's the formation of an alkene, a double bond. So what we're basically doing here is the same arrows as an elimination, right? But we're just doing it one carbon closer, right? Instead of, normally what we say is at the alpha carbon, we go to the beta carbon and we eliminate. Now we're saying that at the alpha carbon, we also eliminate. So this is an alpha elimination, right? What we're going to see is that something in solution will just pick this H up, right? Kick that pi bond there. And then that group that we just added onto oxygen, turns out that's also a very good leaving group. And that is going to be our oxidation. So this is what every oxidation is going to look like in this class mechanistically at the most basic form. And without overcomplicating it, I just want you to understand. You turn O into some group with a leaving group on it. Or sorry, some group that's a very good leaving group. You oxidize by eliminating the alpha hydrogen, form the pi bond, and you just kick off the group. There you go. Okay. Most popular guy to do this, right? Who is it that's doing this group thing? CR6, I believe. CR6. Yeah, chromium 6. Chromium 6 will do this oxidation very, very well. Okay. Usually for the alcohol to aldehyde oxidation state, what we use is something called PCC, CH2Cl2. Okay. I want to really emphasize this right now because we will see in a second. This is a very dry reaction, so no water. Okay. So no water whatsoever. Okay. So if I want to turn alcohol into aldehyde, I can do this reaction. You might have also seen you can do this with bleach. So maybe you might see this NaOCl. NaOCl works the same way, right? So in the case of chromium, so PCC, which is pyridinium chlorochromate, that just looks like this here. Pyridine, we'll talk about this later. Pyridinium, it looks like a benzene ring, if you guys know what a benzene ring is, but with like a nitrogen in it. And then chlorochromate looks something like this. Should look something like that, if I remember correctly, like that. Yeah, pyridinium chlorochromate looks something like that. Mostly correct. I think maybe this might be triple bonded too. I don't remember. It's okay, whatever. Something there. The chromium is that group that's going to be added on there. And then the chromium base group is a very good leaving group. So that's what gets pulled off. Okay. So in the case of PCC, chromium is that group, right? It's that thing that attacks alcohol, becomes a very good leaving group. In bleach, it's the chlorine. So you add chlorine to the oxygen. Boom, boom, boom. Chlorine, good enough leaving group, it'll do it. Okay, cool. All right. So for the aldehyde oxidation state from a primary alcohol, right, all you got to do is add in some PCC, right? And that'll give you the aldehyde. Okay. But remember, we can also turn the aldehyde into a carboxylic acid, right? Because we still have this hydrogen here. We still oxidize that hydrogen. Okay. Now we're still going to use a chromium reagent. So I'll put here a chromium reagent. But there's something special about this chromium reagent, and not necessarily about the reagent itself. It's just maybe in the slurry, right? Remember, in this oxidation, we're oxidizing alcohols. Aldehyde isn't an alcohol, right? It's an aldehyde. So if I want to do an oxidation, I've got to turn the aldehyde into an alcohol somehow. And the way that we do it is we add in water. So many, many ways you can see this written actually. But if you see chromic acid, so HCrO4 with a aqueous sign, aqueous means water. Sometimes you'll literally just see water. Another way you'll see this written sometimes is Jones reagent. That's also a possibility. Sometimes you'll see Jones reagent. If this is written out, you'll see Na2Cr2O7 and then water. Okay. I mean, what's the common feature in all of these, right? It's the fact that there's water, right? Again, so what is this water doing? Again, you probably don't need to know this, but I like to show it because it helps you out, right? Water adds to the aldehyde to make two alcohols. So hey, now we've got all this oxidation that's possible, right? Because now we have our alcohols. So you can imagine very briefly, right? A group adds to G, and then this hydrogen is eliminated out, right? And that forms the carboxylic acid. Okay, so for a primary alcohol, right, we have available to us basically two oxidation states, right? We can go from alcohol to aldehyde. And if we wanted to, we can go aldehyde to carboxylic acid. Okay, so to kind of summarize this on the next page without all the drawings, I suppose, all the mess, right? We can go from here to here doing that PCC, CH2Cl2, right? And then we can go from here to here. I know I'm kind of drawing it a little bit weird. I guess I'm just trying to show you guys where the group is, right? Or like how to think of the alcohol, right? This would just be HCrO4 and I'll say aqueous here. Now, remember, I mentioned that this had to be dry, right? This had to be totally dry. It's because it turns out that, I mean, think about it, right? If the only difference between these two is that they're dry, they both have the same, active ingredient, which is chromium, right? The only difference is water. Then even a drop of water in this PCC reaction is going to convert this alcohol directly into the carboxylic acid. So you don't actually have to even go through the aldehyde. Like you don't have to separate out the aldehyde. You can just do, I mean, if you're cheeky, you can do PCC and water, but none of us want to be cheeky on the exam, right? We just want to get our points. What you can do is you can do HCrO4, aqueous or water, and you could instantly install the carboxylic acid. These reactions are the best. All you do literally is on that carbon next to the alcohol, just draw a double bond. So you could have something as crazy as this with all this monstrosity. But if you know that you're doing HCrO4 aqueous or whatever condition that is wet, just put that carbonyl right there, make that carboxylic acid, call it a day. Everyone's very happy. Okay. So really, if you think about it, the oxidation that matters, because carboxylic acids are so easy to make, you just kind of, you just you bring your water bottle into lab and you drop a little bit of water into your mixture, right? This is really easy to do, right? What's going to be a little more difficult is the PCC because you have to, everything has to be dry. Now I've actually done a PCC oxidation. It is a nightmare. It is very, very difficult because you have to oven dry everything. You have to make sure no water is anywhere. If there's even a little bit of water in your stir bar, you have accidentally over-oxidized. It's just going to happen. Okay. Cool. So primary alcohol to aldehyde or carboxylic acid, totally accessible, right? Just depends on your water content. You're using chromium for both. Sorry, you're using chromium for both, right? It's just a matter of how much water is involved. Okay. Cool. Now here's a cool little tidbit, right? Because I want to make this fun. I want you guys to take something out of this that you can maybe tell your, maybe particularly tell your drunk uncle or your drunk aunt, or your drunk cousin or anyone that is drinking, because this is a cool little thing, right? Alcohols are alcohol, right? I mean, like the alcohol that we drink is an alcohol. It is ethanol usually ethanol. And a lot of you guys are probably familiar with on TV shows or just, common knowledge from word of mouth that, if you drink a lot of alcohol, you get very drunk. And getting drunk is not very good because maybe you have to drive a car, right? Maybe someone makes a mistake. They get in their car and they drive and they get pulled over, right? How does the officer know that you've been drinking? Maybe he smells it, but remember, there's a legal limit, right? We need it. You can't just be like, oh, I smell a lot of beer on you. Let's go to jail. That'd be very wrong, right? That's not a very good thing to do at all. But we do have a quantitative machine, or police have a quantitative machine that can help them. They have the breathalyzer. So let's say our friend here, Timothy, not related to Jimothy, right, drank a little too much and he got behind the wheel. Uh-oh, right? What's going to happen to him when he gets pulled over by the police? Well, the police are going to give him a breathalyzer, right? Because maybe the police like kind of recognizes, hey, I smell, alcohol on your breath. Hey, I smell alcohol on your breath, right? So he gives them a breathalyzer. A very good artist, by the way. And so Timothy has to blow on the breathalyzer. Okay. So let's think about this. So I just mentioned that alcohol, right? Alcohol is an alcohol, right? So maybe it's ethanol. So maybe it's ethanol. So you have, maybe let's say you have a lot of ethanol in your breath, right? What can this machine do to detect how much ethanol that you have on your breath? Well, maybe I can use a metal, because metals give off a color when they are reacting, right? When they go into different, whether you go from, a certain oxidation state to another, they can give off a color. And maybe there's a metal I can react with ethanol that can do a specific transformation. Hopefully you guys see where I'm going with this. If I use CR7 or CR6, right, and turn this into ethanol, right, well, that is an oxidation of the metal, right? Or sorry, the oxidation of the alcohol, which is a reduction of the metal. That metal is going to give off a certain color, right? In this case, it's going to give off a certain green color. And because of Beer's law, if you guys remember Beer's law from Gen Chem, right, we're going to be able to see how much concentrated alcohol you have in your bloodstream, right? Isn't that cool? We're using chemistry that you guys learned in 8B to, I guess maybe not so great, right? Because, people are getting arrested. I guess it depends. It depends on where you're on that. Anyways, it's pretty cool that we can break down this machine. And maybe the next time you get pulled over, you can say, officer, I haven't drank that much organic water. In fact, I can tell you exactly how that machine you're making me blow in works, right? You're blowing on a metal that's giving off a certain color of green. And then using Lambert's, or I think it's Lambert beer or something like that, beer Lambert, using that law, which tells you that, color and concentration are correlated, right? Machine will tell you exactly how much alcohol is in my breath, right? Isn't that pretty cool? I think that's pretty cool. Okay, so cool little tidbit there. Right. All right, cool. So story time over. So just to kind of summarize, right? Primary alcohols, which I'll kind of draw like this now. Right, we can do a single oxidation to the to the aldehyde state. That's a dry PCC. CH2Cl2 is just a solvent. Or if I wanted to, I can go all the way to the carboxylic acid. Right, that's just, I guess if I want to use my little trick to make it easier, right, that is just putting a carbonyl here, making the carboxylic acid. Just use something aqueous, right? PCC water or HRCO4 aqueous, right? Sorry, let's expose you guys to newer things. So Na2Cr2O7, H2O, H2SO4, something like that. That'll work, right? You could also do the same thing to get to here, right? It's no big deal. Okay. So primary alcohols have the ability to oxidize a lot. Secondary alcohols can also oxidize, but there's only one hydrogen here. So regardless of what you use, whether it's wet or dry, who cares? There's only one possible oxidation, right? You get to the ketone. Who cares? So just use any chromium you can use. Again, this is Jones reagent. This is just PCC. So I guess I'll write here PCC, wet or dry, doesn't matter. You'll only get to a ketone. You cannot at all access the carboxylic acid state. Impossible, not going to happen. Okay, because there's only one hydrogen there. This has two hydrogens, right? That's why we were able to facilitate those two. First one to aldehyde and then the second one to carboxylic acid, right? So we only have one here. Which then leads us to the tertiary alcohol, right? 2 seconds. What's the answer of any oxidation, right? Answer is NR. There is no hydrogen. So maybe a good problem tomorrow, or sorry, on Monday will be, hey, I have this alcohol and I put it in PCC, right? Dry PCC. What's going to happen? Maybe take pause and think about it, right? What I think is going to happen is that the side where we have hydrogens, right? PCC means that we only oxidize one of them. Get an aldehyde here. We get an alcohol on the other side. That one never oxidizes. That's a good question, right? Maybe we did it in Jones so that then it's a carboxylic acid, right? It's going to depend. Could also just be that we have a primary alcohol and a secondary alcohol, right? That is going to give us a carboxylic acid and a ketone if I did this in Jones, like some aqueous chromium. Okay, cool. All right, well, with that being said, let me quickly peruse through, again, shout out to Maurice. Maybe we can start a little game where people can, the messier, I don't really care how messy notes are. Maybe we can play a little game where you guys can send me notes in and maybe draw something funny or something and I'll feature them. Maurice didn't really draw anything funny, which is okay, not on them. I didn't exactly ask them for it, but that'd be a fun little game to play. Maybe draw something funny. I'm a good artist, I think. And it'd be pretty fun. Maybe you can play a little game and the person who has the best drawing, I don't know, wins like some kind of virtual e-coin or something. I don't know. We'll make something up. But yeah, I think I'm just kind of scrolling through this really fast, but I think I've covered everything we've talked about. Yeah, probably as much as we need to know now. Cool. All right. So again, if there's any questions, do let me know. I imagine this was a little fast. I do agree with my a little too fast. Kind of condensed 5 lectures, so 5-hour lectures into about 2 hours. So please let me know if anything's confusing. Yeah, cool. All right, you guys have a good one. See ya.